Welcome everyone. Today we're going to do a deep dive into asynchronous programming. We're going to trace the whole story, starting way down in the operating system kernel and pulling all the way back up to the code that you and I write every single day.
Okay, before we jump in, just a quick note on how this deck was put together. We did use some AI assistance to draft it, but, and this is the important part, it was all heavily guided and reviewed by senior engineers. So think of this as a very structured, human-curated summary, not, AI slop.
So here's our game plan. First, we're going to start high level with the big trade-offs in concurrency to really get why we even bother with async. Then we're going to dive deep, right into the OS kernel. After that, we'll pop back up to look at the event loop, the language itself, and wrap up with some really critical performance patterns and pitfalls.
All right, let's kick things off. Before we get into the nuts and bolts of how async works, we really need to understand why it even exists. And that conversation has to start with the different ways we can handle concurrency. This table lays out the core trade-offs perfectly. You've got your simple, synchronous model, easy to write, but it just doesn't scale for I/O. Then there's multithreading. It's fantastic for heavy CPU work, but it costs a lot in memory for each thread, and suddenly you're dealing with headaches like deadlocks and race conditions. But then look at the async model. For high I/O, it's a superstar. Highly scalable with incredibly low resource overhead per task.
And this really is the crucial point, right? The model you choose depends completely on your workload. Async is tailor-made for I/O-bound work. That's any task where your program is just sitting around waiting for a database query to return or a file to be read. Instead of letting the CPU just twiddle its thumbs, async lets you use that idle time to get other work done. For raw number crunching, though, multi-threading is still your best bet.
I love this analogy because it's so intuitive. A synchronous chef would make the soup from start to finish, then clean up, then start on the salad. But the asynchronous chef, they start the long-running task, the simmering soup, and immediately pivot to chopping vegetables. They're not just waiting around. It's all about maximizing your throughput by making sure your resources are never idle.
Okay, so we get the what and the why. Now let's go down the stack and see how this is even possible. And it all begins deep inside the operating system kernel.
So your application, your Node.js server, your Python script, whatever, it lives in what we call user space. You can think of this as a safe, restricted sandbox. It's designed this way for stability. Your code can't just directly talk to the network card or the hard drive.
To do anything useful with the hardware, your app has to ask for help from kernel space. This is the core of the operating system. It's got all the privileges, all the drivers, and direct access to manage the system's hardware. And the bridge, the gatekeeper between these two separate worlds, is the system call. When your app needs to do some I/O, it makes a system call. This triggers a very controlled, secure switch into kernel mode. The kernel does the heavy lifting and then hands the result back. This handoff is the fundamental building block of non-blocking I/O. And what's really fascinating here is that different operating systems have different philosophies on how to handle this. On one side, you have Unix-like systems with Epoll or Kqueue. They use a readiness model. The application essentially asks the kernel a question. Hey, here's a list of connections. Just let me know when any of them are ready for me to do something. On the other side, you have Windows with IOCP, which uses a completion model. It gives the kernel a command, go perform this entire I/O operation for me, and just ping me when you're completely done.
Okay, with that kernel foundation solidly in place, let's pop back up into user space and see how runtimes like Node.js actually build on top of these powerful OS features. And that brings us to the event loop.
The event loop is really the heart and soul of the asynchronous model. The best way to think of it is as a central traffic controller. It's just a continuous loop that keeps asking the OS, hey, got anything new for me, using those tools like Epoll. As soon as the OS reports a new event, like data arriving on a network socket, the loop wakes up, grabs it, and schedules the right piece of your code to handle it. Now, a really robust event loop, like the one in LibUV, which powers Node.js, isn't just one big messy queue. It's actually made up of distinct phases that run in a very specific order. First, it'll check for any expired timers. Then, it'll pull for new I/O events. Then, it'll run set immediate callbacks, and so on. This strict ordering is really important because it guarantees a predictable execution flow and prevents certain kinds of tasks from hogging all the resources.
And this right here, this is a critical detail that trips up a lot of people. While LibUV uses the true non-blocking magic of the OS for things like network I/O, not everything at the OS level is actually non-blocking. A great example is standard file I/O. So what does LibUV do? It kind of fakes it. It maintains a separate, hidden thread pool in the background just for these blocking tasks. It's a really clever trick, but it's an important abstraction to be aware of.
All right, we've gone from the kernel all the way up to the runtime. Let's finish this journey by looking at the part we interact with every day, the programming language itself. How have languages evolved to help us manage all this complexity?
The evolution has been pretty incredible to watch. We started with callbacks, which quickly led to the dreaded pyramid of doom, or callback hell. Then came promises, which were a huge improvement, letting us chain asynchronous actions together in a much cleaner way. And finally, we landed on async await, which makes async code look and feel almost synchronous.
You can see the progression so clearly here. With callbacks, error handling was a mess, and the logic was just hard to follow. Promises fixed a lot of that by giving us .catch for centralized error handling and a more linear flow. But async await? That was the real game changer. It's really just syntactic sugar on top of promises, but it lets us write code that's incredibly intuitive and use the standard try-catch blocks we're all used to.
So, now that we have this complete, full-stack picture from the kernel all the way to our code, let's talk about performance, and specifically, the single biggest, most common mistake that you can possibly make.
This is it. This is the cardinal sin of async programming. Remember, all of your JavaScript code runs on one single main thread. So if you run a long, synchronous, CPU-intensive task, you block everything. The entire event loop just grinds to a halt. No new network requests can come in, no timers can fire, your application is effectively frozen until that task is done.
And these are the usual suspects. A big, long-running calculation, using a synchronous file read API instead of the async version, or even a really badly written regular expression that gets stuck in what's called catastrophic backtracking. Any one of these can completely tank your application's ability to respond.
So what's the solution? The best practice is to embrace a hybrid model. You have to use the right tool for the job. The event loop is an absolutely world-class I/O dispatcher. Let it do that. But for any of that heavy CPU-bound work, offload it. Shove it into a separate pool of worker threads. That way, you get the best of both worlds, unbeatable I/O scalability and true parallel processing for your computations.
And I'll just leave you with this one question to think about during your next architecture review. Almost every real-world application is a mix of I/O-bound and CPU-bound work. So the question is your architecture designed to handle that reality? Thank you.